over to you.
Right, so hello everyone. I'm Ralph Potter. I'm a research engineer at the Centre for Digital Entertainment at the University of Bath and also with Codeplay. And I'd like to talk to you today about kernel composition in Sycl. So Andrew talked about building template libraries on top of Sycl. And he also talked about the challenges of not being able to do dynamic construction of kernels in Sycl. So this is some work we've done in that sort of area. So if we start with an introduction, GPU programming remains hard. So we've got an audience today with a great depth of knowledge of OpenCL, but there's a whole raft of programmers out there who don't have that knowledge. And for them, they want libraries and easy ways to access the power of OpenCL. Now you can produce a library of kernels, of primitive kernels, such as OpenCL IPP, and you can give them to developers. But then there's a problem with composition. You as the library developer cannot predict every possible combination of kernels that your third-party developer might want to use. Now in OpenCL, you can resolve that with runtime construction. You can do something like Halide or ArrayFire, where you produce a domain-specific language in C++ that under the covers does string manipulation to construct a kernel. That doesn't fit very well with Sycl's offline compilation model. So Sycl does have OpenCL interop. You could get that to work, but philosophically, it doesn't really fit with how Sycl works. So we've gone for something a little bit different. So we started this work 18 months ago with a set of motivating questions. Sycl was still being defined. We needed to know, was Sycl sufficient to build higher level template libraries? Could we do kernel fusion in Sycl? Was C++ enough to do that, or did you need extra tools? And could we construct kernels from simple primitives? So that's where we start. So if we have a piece of work we want to do, in this case a really trivial example, a fuse multiply add. Multiply two numbers, add another one. As an OpenCL C developer, we might write a kernel like this. And we end up with 3 loads, 1 store. It's not a bad attempt. But if we try and use OpenCL IPP and this collection of primitive kernels that a less familiar developer might go and download off the internet, we find that there's no fused multiply add kernel. So now we have to run 2 kernels with an extra load and an extra store in the middle, and the performance is not great when we start doing that. So again, we can resolve this through runtime construction. We can produce a library that dynamically constructs an OpenCL C kernel for us. The library author has to put the compilation machinery into the library, but we can do it. We still have this thing about that we've said several times over the conference about weak typing between OpenCL C and C++A. But these things exist. Halide's out there. It works. It gets decent performance. Now, when we come to approach this in Sycl, there are some constraints in Sycl that inform why we did the work we did in the way that we did. So Sycl is static offline compilation. You're going to use a command line compiler, compile down to some, it might be a device binary, it might be down to spear, it depends on the runtime. You've got a restricted subset of C++11 within the kernels. It's the usual restrictions that multi-coreware talked about or Andrew talked about. No function pointers, no virtual functions, no dynamic recursion. You can do templated recursion, but you need to know when you're going to terminate the recursion. Another thing that we have in Sycl is that if a variable is referenced inside a kernel lambda, it's implicitly copied into the kernel arguments. Now we use this in our examples that you'll see later, but I will add a caveat here, which is if you have a large data structure, wrap it in a buffer and pass it through an accessor, because the kernel arguments end up in private registers. And if you just blindly copy a 10,000 element matrix, your registers are going to be gone. And the last caveat that we have is that accessors are required to do the scheduling in Sycl, but they can only be declared in a very specific scope in Sycl at the point when you're submitting to a queue. So you declare an image in your host code and you turn it into an accessor later on. And that will again inform some things that we have to do when we construct this higher level representation. So our approach is to use C++ templates to define a domain-specific embedded language. We focused on image processing as a use case, but you could generalize what we've done to other fields. We capture the syntax of the expression in the type, in the C++ type system. Boost Proto does an awful lot of the heavy lifting for us. So Boost Proto is a library for building domain-specific languages in C++. And it just so happens that all of Boost Proto compiles on Sycl, both for device and host without problems. So here's an example of what we end up with. So for our really simple fused multiply example, we declare some operands, just 4 images, and then we write out our expression. And our expression looks a lot like the mathematical expression we're trying to achieve. And we take that expression and we feed it into an evaluation function along with a Sycl queue and a ND range and our set of images, which we will substitute A into the _1 and B into _2 and etc. And when we execute that, what we end up with is a Sycl kernel, which compiles down to OpenCL, that runs in parallel on our device. So our end user only really has to understand how to write that expression and how to call eval, and they're done. So how do we make this thing work? The first thing to note is that that expression statement returns what looks like a really complicated C++ templated type. Actually, that template maps quite cleanly onto the AST, the syntax tree, for our original expression. And we're going to apply some manipulations to that to get it into a form that we can then run on top of Sycl on our device. So our DSL eval function that we saw at the bottom of the first example does a number of things. We replace the placeholders, the _1 and _2, with real values. We transform images and buffers into Sycl accessors so that we can use them inside the kernel. We examine the structure of the expression and we figure out where we're reading from an image. We're going to have to insert an OpenCL read image instead of just blindly treating it like a variable. Also, our expression tree has used C++ reference types, but if we were to copy those to the GPU, which has a different memory space, those reference types aren't going to make sense. So we'll have to do a transformation to turn those into actual values. And then Sycl will do the heavy lifting of copying our transformed expression to the device and doing the parallel evaluation. So the internals of that eval function look something like this. We take a queue, which we're going to submit some work to, a template argument, which is our expression. We don't need to know what that big complicated type was. We can just pass it as a template argument and not think too hard about it. We'll apply some compile time transformations inside the queue submission lambda. So this is still executing on the host. That's how we do the transformation from an image to an accessor, for example. Boost Proto will do the copy to get rid of our references and turn it into actual values. And then we reference that copy variable, which is still some complex C++ type, but we reference it inside our Sycl kernel. And because we've referenced it inside our Sycl kernel, it gets copied into the kernel arguments. And finally, we have this DSL context, which contains the actual implementation of our primitives. So where we had a plus inside the DSL context, there is an implementation of add two elements together. So how do we do our transformations? Proto gives us a lot of the mechanics. For this, we can define a type which will pattern match on the expression tree and then call another compile time operation wherever it finds something that matches this pattern. Now, I've cut this example down a little bit to make it fit on the slide. You wouldn't always want to turn an image into a write accessor. you'd actually want to analyze whether it's the left-hand side or the right-hand side of an assignment. The grammar is a little more complex. But this happens almost all at compile time. There is a little bit that you have to do at runtime. Your image arrives at runtime, so the actual construction of the accessor has to be runtime. But figuring out what you're going to construct, the compiler will do that at compile time and optimize it all away. So this is the sort of thing I'm talking about. We can start off with a simple assignment. We have an image on the right-hand side, a float-for variable on the left-hand side, and we're going to transform it so that the assignment becomes a write, the image becomes a writable accessor to an image, but the float variable remains the same. We don't need to transform that in this particular case. And then finally, we get to evaluation, which happens inside the Sycl kernel. And here, the boost proto-eval maps our transformed expression tree to primitives at compile time. So the generated spear that I get out of the end of, say, that fuse multiply add is literally the 3 loads, the 1 store, the multiply and the add, and a couple of get global IDs. There's no big traversal code that gets emitted into the spear. It actually comes out very close to the spear that you get from the handwritten OpenCLC. So, on to evaluation and our results. So we use Codeplay's Sycl implementation, where the device compiler will generate spear 1.2. We evaluated on the integrated GPU and an AMD Kaveri processor. Input images were 4K by 4K images, 4 channels, 8 bits per channel, so integer data. If we look at an unsharp mask is an image processing technique where you're going to take the difference between a Gaussian blurred version of the image and the original, multiply it by some weight to give you a weighted version of the high frequency details and add that back to the original image. If we want to express that in our DSL, then it looks like this. And again, our expression looks pretty similar to the mathematical definition. And beyond that, all we're doing is declaring operands and calling an eval function. It doesn't require a great deal of knowledge from the end user to get it up and running. So when we decided to evaluate performance, the first question that comes up is the performance of the primitives the same in OpenCL IPP, in Halide, which will do dynamic fusion of kernels, and in our Sycl implementation? We tried to implement the primitives in the same way. So we looked at OpenCL IPP, we took their implementations, we translated them to C++. And in general, the primitives have the same performance as the OpenCL IPP ones, with one notable exception. Our Gaussian blur ends up 30% faster. Well, why is that? Turns out that it's to do with the compiler chain. The Halide version and the Gaussian version generate OpenCLC and feed it into AMD's OpenCL runtime, which generates one set of AMD IEL. Our version generates C++, feeds it into Clang, compiles it offline, and generates Spear. And when you analyze the intermediate layer that's generated by the AMD runtime, we find that the offline compilation, one loop didn't get unrolled, but it did get unrolled by the online compilation. I guess we're just lucky to land on the right side of that performance difference there. For why the Halide ones are slightly slower is to do with how Halide interprets images as arguments. We had to have some explicit typecasts in there, which involves a little bit more work for them in that example. So if we move on to the fused expression, and we look at OpenCL IPP as our base case, there, to implement the Gaussian, we need 4 kernels. We've got the cumulative amount of time. If we do the same thing with Sycl as individual component primitives, the performance would be the same as OpenCL IPP, except for that faster Gaussian where we just got lucky with the optimization. But then if we look at Halide and Sycl where we've fused the complete expression, where we haven't manually broken things into their component parts, then we find that Halide does perform faster than OpenCL IPP. We have eliminated intermediate memory accesses, but the Sycl version performs even faster. Some of that is down to our Gaussian. Some of it, I would speculate, is down to compiler optimizations. It's somewhat difficult to get to the bottom of exactly why it's that much faster than the halide version. So in summary, we've composed kernels from simple primitives using a domain-specific language that we've built in C++ on top of Sycl. We get strong typing because it's C++ all the way down. Expressions in our domain-specific language generate one kernel, so we lose the intermediate loads and stores that we might otherwise have if we were using a collection of kernels from a primitives library. And we're using compile time transforms to map our DSL down to SPEAR via Sycl with a pretty minimal runtime overhead. So we're not seeing kind of traversal of the expression tree inside the kernel. That all optimizes away. So on that, if there's any questions.
Great, thank you, Ralph. Let's thank our speaker. And then first question down here, yeah?
So the halide paper contains like pretty complex filters.
Yep.
Like, have you tried to implement those?
So we haven't gone anywhere near as far as halide do. And the other thing that we don't do is the halide paper also does a lot of work on scheduling and allowing you to choose how you optimize the work. For our performance numbers, we did our best to optimize the answer, but we don't have a similar thing in this work. So there are some more complex things we can do with the DSL that aren't covered here. We can do compound statements and that sort of thing, but it's nowhere near as advanced as halide in terms of the algorithms you can express.
Okay. All right, thanks.
Any more questions from further back in the room? Does everyone want lunch? Is that what it is? It's probably good. It was good yesterday.
Come and speak to me afterwards. It's not up online, and Codeplay sponsor me, so it belongs to Andrew, but come and speak to me afterwards.
Talk to this guy. Well, in that case, amazingly, we're going to finish a couple of minutes early, so you get slightly longer for lunch. We'll be back at 2 o'clock for the afternoon sessions. Lunch is going to be served just outside, and